everybody. In the previous video, we stopped at the generator which operate together or parallel operation of synchronous generator. So we said when the two generators are operate in parallel, that means they will share the same load. It's not like in the state of alone operation. So the generator will be responsible to feed the load. But if you have more than one synchronous generator, like generator 1 and generator 2, so two generators here are going to supply the same load, and they are going to share this load based on their rated power and based on their frequency when synchronous to the grid and so on. Okay, so if the total power, for example, is 10 megawatts, so they will share it by a ratio depends on their rated value, rated power, or also based on their frequency until they reach to, I mean, they can, if the two generators are the same, that means they have the same aspect, the same rated power, the same frequency, and they can share the load 50-50. Okay, but if one generator is small, one generator is big, so the bigger generator will take the bigger load and so on. Okay, so they are going to share the P out, the P total as a real power, and also they are going to share the reactive power, which is Q total here, into Q for generator 1, Q for generator 2. Here we have one example actually to show how these two generators are going to share a load. So he said there are two generators are set to supply the same load, so they are working in parallel to set or to supply same load. Generator 1 has a no load frequency of 61.5, so this is the frequency in the case of no load. No load means the generator not yet engaged with to the grid, it's not supply the load yet. Okay, and the slope of SP1, and you know slope actually it is it's the slope of this line, for example. So when we talk about the slope, that means how this the value of the output frequency here will be changed with the power. The slope of the generator here represents the relation between the frequency in the y-axis and the power or real power here, which is P in the x-axis. And usually you know the slope here, the formula for slope is equal to y2 minus y1 over x2 minus x1. So slope usually give you the value of the y-axis, the second value. That means when we talk about y2, that means this value, this is y2 here, this represent y2, and this one is represent y1, and this point represent x1, and this point here, or the 0 point, represent the value of x2. So when we talk about the slope, that means the relation or how the output will be changed with a change in the input. So he said the slope of this line, is equal to 1 megawatt per hertz. So for any change in the frequency by 1 hertz, we have change in the power or the output power of 1 megawatt. So if we increase the frequency by 1 hertz, the output power will increase by 1 megawatt. Okay, generator 2 has no load frequency of 61 hertz. So this is the no load frequency. You can see here this 61, and here we have 61.5. That means F1 does not equal to F2. The frequency of the first generator is not exactly the same as the frequency of the second generation. So I mean generator. So the second generator here has lower frequency, and also, but the slope is the same for both. So the slope is 1 megawatt per hertz. The two generators are supplying the real load of 2.5 megawatt. So this is the total load, which is 2.5. If the frequency of these two generators are the same in the no load, that means this will be 61.5, this one is 61.5, they will share this 2.5 exactly the same. So each one will take 1.25. But since the frequency of each generator is different, so we need to calculate how they are going to share this load between each other. Okay, and he gave you here the power factor is 0.8. Actually, the question is find the system frequency and power supply by each generator. He wants to know the B of generator 1 and the B of generator 2, how they will divide the two, or how they will divide the 2.5 here between generator 1 and generator 2. Okay, then assuming that the additional load, he assumed that there is one extra load, that means that 2.5 become 3.5 megawatt is attached to the power system. Find the new system frequency. You want to know what is the new frequency. The first frequency, for example, is in the no load one, 61.5 and 61. You want to know what's the new frequency when we increase the load to 3.5. And you want also to know the BG1, BG2 again for the two generators when the load is increased. With the additional load attached, it means with the 3.5 megawatt, find the system frequency and the generator power. When we say system frequency here, we are talking about the grid frequency, the frequency of both generator. We said last time when we want to connect two generators together, they should achieve to the same generator, or at least the new generator should have a little bit higher frequency with the grid, or to the existing grid or existing system, so it can be synchronized with the grid. Otherwise, it will cause the reverse power. For that, we said here, you want to know what is the grid frequency. The grid means you have this bus bar here, and you have G1 and you have G2. Both are connected to the same bus bar. Okay? To feed the load, and the load will connect it from the bus bar here to take to the load. So there is one formula here. You need to know about the power and the relation between the power and the slope and the frequency of the generator. Okay, so power equal to the slope times frequency no load minus frequency system. Frequency no load means the frequency of the generator that we want to connect to the grid. Frequency of the system is the frequency of the grid. Okay, when we connect more than one generator. So you can see here, for the B load here, should be divided between B1 and B2. That means B1 for generator 1, B2 is for generator 2. If we apply the formula here, to substitute the value of B1 and B2 based on this formula here, which is P equal to SP, F no load, F system. So we have P1 equal to SP1, F no load 1 minus F system, while B2 equal to P2, SP2, F no load 2 minus F system. So we have F no load 1 and F no load 2. F no load 1 here, F no load for generator 1 equal to 40, is equal to 61.5. F no load for generator 2 equal to 60, sorry, F no load. Wait, I want to remove this. Okay, so you can see here, F no load for generator 1, for the P1 is equal to SP1 times F no load 1. This is for generator 1, which we already know that is equal to 61.5 hertz. F system, we don't know. We don't know the new frequency that we will get after we connect the two generators together. I know the frequency of the first generator, and I know the frequency of the second generator, which is 61 hertz. Okay, but I don't know F system. F system, that means the new frequency that we will get after we connect the two generators together. Also, I have slope for generator 2 here. The slope is equal to 1 megahertz, 1 megawatt per hertz for both. It's 1 megawatt per hertz for both generators. So this for generator 1, this for generator 2. Okay, we just substitute for these values. We have the total load here. We know the total load is equal to 2.5 megawatt, and we want to know now the missing value is only the F system. So if we want to find the F system here, we need to open this one in order to make just to solve in term for the F system. When we solve for F system, the new formula gave you F system equal to SP1 F no load 1 plus SP2 F no load P2 minus P load. This the P load will go to the other side, okay, and the F system will go to that side, to the left, and P load will go to the right. After we consider the value, after we open all these brackets, okay, SP1 plus SP2. So we just substitute for the value of the slope, the value of the no load frequency for generator 1, slope for generator 2, no load frequency of generator 2, and the value of the load, which is 2.5 megahertz. So since our slope in megahertz per in megawatt per hertz, so just leave it in megawatt. Okay, don't no need to change to watt or to kilowatt and so on, because this formula or this value is 1 megawatt per hertz. So just leave it megawatt. Now we solve, we find the frequency of the system is 60 Hz. Since the frequency of the system is 60 Hz, I can calculate what is the value of the supplied, how the load will be shared between generator 1 and generator 2 based on their frequency. So just I rewrite the previous formula, P1 equal to SP1, F no load 1 minus F system. I substitute for value, this 61.5, this one is 60, and SP is 1. So I got the value which is 1.5 megawatt. And the second one is 1 megawatt. We can see here the second generator takes lower load than the first generator. Why? Because the frequency of the first generator is higher than the frequency of the second generator. Since the frequency is higher, so the load will be also higher. Okay. If we increase the load on that generator, its frequency will be dropped. So this is how the two generator will share that 2.5 megawatt. Each one will take the first one will take 1.5 and the other will take 1 megawatt. When we go to the next part here, we want to know if we increase the load to 3.5, that means we increase 1 megawatt, how the new system will share, how the generator will share the new load. So we apply the same formula, which is F for the system equal to SP1 and so on. We just replace the value of the P load here. So this P load will be different from the previous part of the question or of the example. So it become here 3.5 instead of 2.5. And the new frequency that we got, that means if we increase the load on the system to 3.5 megawatt, its frequency or the frequency of the system will drop by 0.5 hertz. So the new frequency will be 59.5. Then we substitute here in the equation to calculate how they will share the load. You can see here the first generator also takes 2 megawatt and the second will take 1.5. So here the total is 3.5 megawatt. Okay. The third part of this example, which is if the no load frequency of generator to increase, that means the system frequency. The question is, with additional load, which is 3.5, find the system frequency and the generator power if no load frequency of G2 is increased to by 0.5. That means the frequency of the second generator is increased by 0.5 hertz. 0.5 hertz from its new frequency, which is here. Its new frequency is, it was 61. It is 61 hertz, but it becomes 61.5 now. So now this is 61.5, this one is 61.5 as exists. So the total frequency in this case will be 57.75 instead of 59.5. Okay, so now you can see, since the frequency are the same, which is 61.5, the load will be the same. For P1 will equal to P2 because the frequency are equal, so the load will be equal. So each generator will carry on 1.75 megawatt. Okay, this example actually about how the two generator can share one load and what's the impact of the frequency on the load on each generator. Now we move to the next part of this chapter actually, which is more on the synchronous motor. We already talked about the synchronous generator here. So now we move to the synchronous motor, and we said most of the application of synchronous machine is as a synchronous generator, but we still have some of machine are used as synchronous motor. Okay, so usually the synchronous motor here or the principle of operation of synchronous motor, since for synchronous machine we have a separate DC field source. So the field source or the DC field source, which is which feed the current into the rotor here, and to generate the BR from a DC source. This is for the rotor. We have one magnetic field. We call it PR. Okay, or magnetic field which goes by the rotor of the machine. In order to run this synchronous machine as a motor, we need also to apply another electrical source to the stator windings. So we have BS from the stator and we have PR from the rotor. So this is BS and this is PR. BS is generated from AC source which is connected to, or a three-phase AC source which is connected to the stator winding, and the PR is generated by using DC source which connected to the rotor windings. Okay, so the stator, which is the armature here in the synchronous machine, we call it armature, and the rotor here we call it the field. Okay, so we have two magnetic fields. Since you have two magnetic fields, these two magnetic field, there is an angle between them. For the difference between them will give you the synchronous speed here. So always the rotor try to catch up the magnetic field generated by the stator. So for that, since we have two magnetic field, we have a torque, and this torque will cause the rotor to rotate. So we have the input is electrical power, and the output will be the torque, which will be taken from the rotor or from the armature. I mean from the field winding of the field of the synchronous machine. Okay. So in the case of generator, we only have one magnetic field, which is on the rotor, and the magnetic field will generate magnetic flux. This magnetic flux, by using induced, it will induce a voltage in the stator winding or armature winding. So we take the power from the generator, but here we give power to the generator stator, then I mean to the machine stator, then we have another power which is the DC source to the rotor. So we have two magnetic flux. Since you have two magnetic flux, that means you will generate a torque, and this torque will cause the machine to rotate. So it's convert the electrical input into mechanical output, or convert the electrical energy into mechanical energy. So the torque of this asynchronous motor will be taken from the rotor part or the rotating part of the machine. Actually, as the synchronous, as the magnetic flux increase, or the difference in this between these two magnetic flux increase, it will produce more torque. So the larger the angle between the two magnetic fields, the greater the torque and the rotor of the machine. The greater the torque on the rotor of the machine. So as this angle is increased between the stator magnetic flux and rotor magnetic flux, the machine will generate more torque, or the more output or mechanical power. So the equivalent circuit of synchronous machine, synchronous motor here, it's the same as the synchronous generator, as a component. So we have the field winding here, we have the field reactors, but for the stator part, which is the armature here, we have also EA, we have GXS, which is the synchronous reactance, we have RA, which is the rotor or the armature resistance here. But the direction of the current in this circuit will be opposite to the generator. So in the generator, the power or the current will go from the machine to the output. So we take V out, we take it from the machine. But here we are going to apply input current to the stator winding. In order to generate magnetic flux, we need to apply three-phase power supply to the stator winding, so we can generate a magnetic flux for the stator. We have another magnetic flux here, so the machine can rotate. So in terms of the component are the same, still have reactance, synchronous reactance, still have armature resistance, but also still have EA, but in terms of the direction of the current, it will be opposite. Also, the relation between the terminal voltage and the internal voltage here, or armature voltage or induced voltage, will be different. Why? Because in the motor, this voltage will be higher than EA. In the generator, this value or this voltage will be higher than the terminal voltage. A change in the direction of current here will cause the voltage here, V output or terminal voltage, will equal to the internal voltage plus the voltage drop across the synchronous reactance and the voltage drop across the armature resistance. So if I want to find the value of the induced voltage on the armature winding, it will be equal to V here, or V terminal minus GXSA minus RA. So that means EA is equal to V or V terminal after we deduct the voltage drop across the two elements, which is the reactance and the resistance. The steady state operation of synchronous motor here, or the characteristic which represent the relation between torque speed characteristic here, we see for the synchronous generator how is the curve between the synchronous speed and between the speed and the torque. And for the in the case of the generator also here, we have the relation between the motor or the machine, the motor speed and also the induced torque. And as you can see here, the speed of the motor is fixed or constant at synchronous speed because we are talking about synchronous machine. So it is fixed at synchronous speed from the no load until we reach to the maximum torque. So tau p pull out here or tau maximum here, the maximum torque that we can get from the motor and here is the zero torque. So from the point of zero torque until the pull out torque, the speed is not changed, it's just fixed. So no change in the value of the speed of the machine here. Okay. Usually the induced torque, it will be generated due to the two magnetic flux, which is the rotor magnetic flux and the stator magnetic flux. When the rotor and the stator are magnetic flux work or meet together, or each one try to catch up the other magnetic flux, we got a new magnetic flux. We call it the delta. And this new magnetic flux, we call it P net. Sorry, we call it the P net here. And this P net actually represent the new or the total magnetic flux after we have the two, which is PR and PS. We say there is an angle between them. This is PR, for example. This is PS, PR. There is one angle between them, and the value of the new magnetic flux, which is produced after we from the two magnetic flux, we call it the net magnetic flux. We already see this equation before, and we said that delta here represent the angle between the two magnetic flux, and also it is the same angle between the VP and EA. We already mentioned this when we talk about the synchronous generator, and we said the maximum torque will occur when this value of delta equal to 90. But we said usually this angle is from 15 to 20 degree only. Okay, so I mean this value will give you the maximum torque or the pull out torque here. If the sine delta, if this delta equal to 90, so that sine delta will equal to 1. Since it's equal to 1, so the total induced will be KPR times P net. If we substitute here or from the relation say tau equal to P over omega, so the value of B actually it is 3VPEA as we calculated before for synchronous generator, and over XS here, and the value of omega is omega M or 2 by NS over 60. So this is how to find the maximum torque of the synchronous motor. And as you can see here, the formula for the maximum torque is occur when the value of the delta equal to 90 and the value of sine delta is equal to 1. The maximum torque actually when the torque on the shaft of the synchronous motor exists, if the torque on the shaft exists the maximum torque or the pull out torque here, so in this case the machine will start to slow down until or because the rotor here can no longer remain locked to the stator, so there will be drop in the synchronous or in the magnetic flux between the rotor and stator, so this will cause the machine to slow down and slave also to stop. And the loss of synchronization here after the pull out torque exists is known as slipping pull. So slipping pull here is caused by the loss of synchronization. Why loss of synchronization? Because we apply torque more than the pull out torque on the shaft of the synchronous motor. So if the torque is more than the pull out torque, it will lose the synchronization between the magnetic flux of the rotor and the magnetic flux of the stator. So this will also known as the sleeping pools. Here is the relation between the IF and IA, and for the synchronous motor here, in the case of synchronous, actually we talk about this characteristic when we talk about the synchronous generator, but the relation there is a little bit different. But here, actually, when we talk about the field and current for the synchronous motor, we investigate the impact of changing the power factor on the relation between the armature current and the field current. So as the field current increase here, we can see the relation, or what happened to the value of the armature current by controlling the field magnetic flux. By increasing or decreasing the field current here, we can see the V curve. This we call it the V curve, which represent the relation between IF and IA. As you can see here, we have three different loads, which is B2 and B1, and also we have here a load for B3, for example. The three loads here, each one is represented by a curve like V curve, and as you can see here, the bottom of this curve, or the minimum value of the armature current, is this point or that point or this point here. The minimum value of the armature current can be obtained at power factor is equal to 1. If the power factor, well, when we talk about power factor or cosine theta here, cosine theta is equal to 1. So we got the lowest armature current, that means the lowest current that will be taken from the source to the stator winding of the synchronous motor. If the power factor if the field current is less than the value which gave you the minimum value here, if in this curve, if the field current is less than this point, which is, we are talking about this part here, in this part actually, we call this area is the motor under excited area. Why motor under excited? Because motor consume reactive power here, and the power factor is lagging. When the power factor is lagging here, the power factor is lagging, that means the motor will consume more reactive power. If the power factor is leading, that means the motor will provide reactive power or generate a reactive power. Okay, so here we have the lagging area, and here we have the leading area, and at 1 we have the ideal case, which is the power factor is equal to 1. So the best is power factor is equal to 1. If the power factor is lagging, so we are under excited. If the power factor is leading, it's over excited. Over excited is good situation actually, because the over excited here will allow the motor to supply bigger torque than the case of power factor 1 or lagging. So in this case, for leading power factor, actually, the generator or the motor here will produce more, or will supply reactive power. Since it will supply reactive power, that means we have a good excitation, we have a good output voltage here, and also we have a good torque can be taken from the synchronous motor. What is the power factor effect, or how the power factor will impact the performance of the synchronous motor here? The ability of power factor adjustment for the power factor, we can control the loads of the power system. Because when we set the power last time equal to VI, don't know, wait, sorry, the power is equal to V times I times cosine theta, and cosine theta is B equal to 3, for example, IV cosine theta. So the value of the power factor here will affect the real power, and also will affect the reactive power of the system. Okay, so the lower the power factor, the greater the losses in our power lines. Why? Because when we have low power factor, that means we have high value of the current, and we have a low or a more voltage drop, more thermal losses, and so on. Okay, since most loads are typically power system here are induction motor, these loads actually have the induction motor usually provide lagging power factor. If you have either inductor or motors transformers, all these will give you lagging power factor. But if you have capacitor, synchronous motor, this will give you leading power factor. Okay, so the good that you have leading power factor rather than have lagging power factor for the following reasons actually. The first one, the leading load supplies some reactive power. If you have a leading load here, this load will supply some reactive power to the lagging load. That means if you have leading load like capacitor or like synchronous motor, this synchronous motor will use to supply the existing reactive power in the system. So if it supply the reactive power in the system, no need to transfer reactive power from the power station to the load, because it will be locally supported or locally fed from the existing reactive power source like the capacitor or capacitor bank or like the synchronous motor. The second, the transmission line carries less current. Why carries less current? Because instead of sending 500 ampere, for example, I'm going to send only 400. Why? Because I have 100 amps for reactive load will be supplied by capacitor bank, for example. Okay, or by synchronous motor. For that, synchronous motor usually used to correct power factor. Synchronous motor are a good tools or a good equipment to correct the power factor of the grid or the power system. The overexcited mode of synchronous motor here increase the motor to maximum torque. As we mentioned before, we said if it's the power excited mode, that means overexcited mode, that means the power factor is leading. So if the leading power factor here, the synchronous motor will provide a bigger load to the grid or bigger torque. Then power factor correction here, we use synchronous motor in order to correct the power factor of the grid. So we call it the process, we call it power factor correction. That means we are going to connect some synchronous motor to the grid, and this synchronous motor will provide reactive power, and this reactive power actually going to feed or to supply the reactive load, which required reactive power like motor, transformer, induction motor, and so on. So it will decrease the loss in the system, and it will improve also the voltage of overall voltage of the system. Since synchronous motor can provide power factor correction here, many loads that can accept constant speed are driven by overexcited synchronous motor. So usually most of the load that require constant speed will be supplied by synchronous motor in the operation mode of overexcited. Why overexcited? Because we said in overexcited we have more torque, and also we have less power losses due to the less the leading power factor.